lesson 3.2, we are continuing to talk about exponents, specifically exponential modeling. So looking at exponential equations and how they relate. You'll see some science tied in today as we talk about growth and decay. I don't think growth and decay are brand new topics to you at all. I think my morning class said they felt like they did some of this last year in Algebra 2, which I think we probably did.
We did.
So, okay. So, exponential population model. If a population P is changing at a constant percentage rate R each year, then this formula applies. So this is going to be kind of our main formula today. P of T equals P naught times 1 plus R raised to the power of T. Now, notice it said that R being the constant percentage rate is R. I said P naught. P of 0. P0. I'm trying to think what other people say. But basically, what I call is P naught, it's your initial population. Population at time 0. Or in other words, the value when x equals 0 type thing. So P naught, P0 is initial population. When we talk about a percent, and we use a percent within an equation, please remember we always use the decimal form of the percent. And as always, T is time. Specifically, we want to think in terms of years there. Okay. As we look at this, depending on your value of R, will determine growth or decay. If R is greater than 0. So if R is positive, then P of T represents exponential growth, if that R is positive, and 1 plus R is the growth factor, because it's 1 and you're adding that percent rate. Okay? If R instead is less than 0, in other words, if R is negative, we're talking exponential decay. And then 1 plus R is your decay factor. And keep in mind that if we're talking R or decay, R is negative. So even though it says 1 plus R, you're doing 1 plus a negative value, which really turns into subtraction. Okay, so there's a little bit of information. I'm going to move right along into example 1 here. Tell whether the population model is exponential growth or decay. And then we're also going to talk about finding the constant percentage rate of growth or decay. So as you look at example A, P of T equals 782,248 times 1.0135, and that is raised to the power of T there. I promise that's a tiny little T.
Looks like a 1.
It's a T, I promise. Now, thoughts? Is this an example of growth? Or is this an example of decay?
Growth.
Why growth?
Because it starts with a 1, so it's greater.
Sound familiar, guys?
Yeah.
Okay. She says it starts with a 1, as in your growth factor. Okay, whatever's raised to the T, it starts with a 1. So that means it has to be 1 plus some number, right? And if it's 1 plus some number, it's going to be growth. If I rewrite this out and kind of expand it a little bit, 782,248 times, that's 1 plus what raised to the T? How could I rewrite that? 1 plus
0.0135.
Yeah, the 0.0135. Okay, and so right there, for that reason, because it's 1 plus that number, it's growth. So the fact that that number there being raised to the power is bigger than 1 tells me it's growth. The fact that it's 1 plus that value tells me it is growth. So this is definitely a growth problem. It represents exponential growth. It asks us to find the constant percentage rate of growth or decay. Where do you find the percentage rate here?
The B for the R. Yeah.
The R value, which is?
1 for that.
Okay. My R value is that 0.0135 because it's 1 plus the R value. Except what is that as a percent?
1.3.
1.35%? Because how do I go from a decimal form to a percent form? To go from a decimal to a percent, you move the decimal 2 places to the right, which makes it 1.35%. Does that sound familiar? Questions there? Okay, well, if you're ready, let's try B. P of T is 1,203,368 times 0.9858 raised to the power of T. Growth or decay? And why are you saying decay? What'd you say? Yeah, this number being raised to the power is less than 1. And if it's less than the 1, that means my growth or decay factor is 1 minus something, and thus a decay factor. So if I kind of rewrite this to put it in the form, 1,203,368 times 1 minus something to the T. And right there, because I'm using minus, that tells me decay. What's that value that goes in there? Yeah, I think that's probably the easiest way, is to do 1 minus the 0.9858 to figure out 1 minus what is 0.9858. What value do we get? No? Did you say 3?
4.
I thought it was going to be 4. I was thinking 0.0142.
I didn't.
1 minus 0.9858.
Okay, yeah, I explained I 1.4.
Like, that's what I've written down in my notes. So if I have it written down wrong in my notes, I definitely need to know that. And that means I did it wrong last year, because these are my 2020 notes. So
I subtracted 0.9868.
okay. Calculator key misstrike. Got it. Okay, so we already agreed that this is decay. And what is that decay, percentage rate of decay?
1.42.
Yeah, if you take this value right here that is R and you change it to a percent, move the decimal 2 places to the right, or as I reminded someone this morning, it's multiplying by 100. So 1.42%. Are we good there? Kind of some basic review, probably, technically. At least I would call it that.
Yeah, so we're doing good.
We're going to keep going. Although the next one's not bad either. So, example 2. Determine the exponential function. So we want an exponential function with initial value 12 increasing at a rate of 8% per year. So we want an exponential function. There's a couple different ways we can do this, but I'm going to go with, we were given a form at the beginning of the lesson, right? P of T equals P naught times 1 plus R raised to the T. What do we know that we can fill in?
15.
We have what?
P, the initial value.
Okay, so what I would say P naught, P0 or P naught, our initial value there is 12. So that's going to go in for P naught. What's increasing, tell me?
Plus.
Yeah, since it says increasing, it's going to be plus, or in other words, the fact that this is a growth example. And it's increasing at a rate of 8% per year. What does that tell me?
0.02.
Yeah, take 8%, change it to a decimal, and my R value is 0.08, 0.08. Okay, so if we write the equation, P of t equals 12 times 1, it's growth, so plus 0.08 raised to the power of t. Can you clean that up just a teeny bit? Yeah, I mean, there's not a lot of cleanup, but we can say P of t equals 12 times 1.08 raised to the power of t. And what I'm going to say, there's several different ways we could express this. In this situation, it just asked us for an exponential function. Did it say we had to use the population model? It didn't say we had. It didn't say we had to talk population, so I just grabbed that because that's the one here. But P of t is perfectly fine. However, you could also just use the generic f of x if you want. And so you could just as easily say f of x equals 12 times 1.08, and this time it'd be raised to the power of x because it was f of x. You could also possibly see instead of f of x, just a y equals 12 times 1.08 to the x. Okay? So all possibilities there. Okay, get what you need there, and I'm ready to move on. Hoping you get a little farther than I did this morning, because, I mean, homework's still due tomorrow no matter where I stop, because I'll get through enough of the next one, but I know they're a little short on what they need to know. Okay. You'll notice the next section says solving exponential functions graphically. But in order to solve something graphically, what do you have to have? You're going to have an equation to graph, right? And so that's kind of where we're going to start here on this one. Because I'm going to help you kind of develop an equation, and I'll show you how it relates to what we already know. Suppose a culture of 100 bacteria is put into a petri dish, and the culture doubles every hour. Predict when the number of bacteria will be 350,000. So not one that we can easily just work our way up to. Okay?
I've done it.
We have everything but what?
R.
Right. And that's the thing. We don't know the R value.
We know if it's positive.
It's doubling,
So it's positive.
so it's
That's
increasing.
As soon as I ask it.
Okay. So I'm going to kind of take you, I want to kind of walk you through a process to kind of develop the equation so you can kind of see where it's coming from, but then I'll also relate it. So let's start basic here. Let's start with where are we at in this scenario after 1 hour? Okay. So what do you know after 1 hour?
It doubles.
We started with 100.
Oh, 2.
It doubles, so we're at 200, yes? Now, bear with me as I write this out. So that means you're going to take 100 and you're going to multiply by 2, yes? I'm going to leave a little gap because I'm leaving myself a little room to expand on my next row. So I could also think of that as 100 times 2 to the first, which, yes, end result is 200. But there's a reason I want you to think of the pieces. How did we get 200? Okay, I'm trying to get you this somewhere. So that's after 1 hour. So now my next question is, okay, Where are we at after 2 hours? Well, if you want to go ahead and give me the end result, after 2 hours, we're going to be where? We have 400 bacteria. But here's my thing. Where did that 400 come from? If you go back here, we had the original 100 times 2 for the first hour, and then what? Times 2 for the second hour. So how can I rewrite that? 100 times 2 to the second. Are you seeing what I'm trying to lead you into here? And I'm going to go one more. So let's do one more and then we'll write our equation. Let's talk about our bacteria after 3 hours. And if we talk after 3 hours, well, are you wanting to give me the end? After 3 hours, we're at 400 times 2, which is 800. But how do we really get to that 800? Pretty much. It's the original 100 times 2 the first hour, times 2 the second hour, times 2 the third hour, which as you're seeing is 100 times 2 to the third. So, do you see an equation here? P of t equals, well, we kind of already knew it was 100, yes? Yeah. They told us the initial value of 100. And then it was 2 to the first, 2 to the second, 2 to the third. We're going to say 2 to the t. So that's the equation we're looking at. And what does that 2 represent? The base. And it's the fact that what's happening to the bacteria. They're doubling, right? So right there, when we have this equation of P of t equals 100 times 2 to the t, that 2 represents the fact that we are in a doubling situation. Okay? Now, I know someone this morning asked, and so I want to kind of make the connection. Up in the original problem, or in the original format, it's 1 plus r, yes? Okay, well, I promise it makes sense. So if this is 100, 1 plus r, well, it's 1 plus 1. Because what happens when you double? You're growing by how much? Right, you're growing by the same thing. You're growing by 100%. If something doubles, it's growing by 100%. And so that's why the doubling is a base of 2, because 1 plus 1, the original 1, plus 100% growth is 2. Does that help make the connection there? So whether you think about it this way or just the fact, anytime you see a doubling, realize the base is going to be 2. Now, we obviously are going to need to graph this, yes? So we're going to graph the equation. Y equals 100 times 2 to the x. And then what are we going to need to do here once we graph it?
Trace.
Okay, trace to where?
350,000.
350,000. That's quite a big number, isn't it? Now, here's my thing. You could eventually trace to 350,000, but we also need a specific answer here. Okay, if you just traced to 350,000, are you likely to land exactly on 350,000? Never when you want to, right? You do sometimes, but never when you need to. And so, if we want to figure out exactly when this is 350,000, we want to know when this equation equals 350,000. Well, the thing is, if we just plug it in here, we're plugging in for y, and that's a difficult equation to solve. So what I suggest you do is you also graph y equals 350,000, which is going to just be a horizontal line, but then what can you do? See where they intersect. Okay, so what we're going to have happening here is we're going to have a graph, and this is just a real basic sketch. We're going to have a graph that goes up here, yes, and then we're going to be looking for this horizontal line and where they intersect. And that is all very doable on the calculator. And I'll take you to it here in a moment once I get mine graphed and showing. But we're going to use second calc and intersect when I lead you to this. Now I should have switched off the yellow. Okay, so I already have mine typed in from this morning. I'm cheating, sorry. Y1 is 100 times 2 to the x. Y2 is 350,000. If I just do a zoom 6, you can see the exponential, and it hasn't even crossed the y-axis yet, but that's because it's going up way steep. But obviously, for obvious reasons, we don't see y equals 350,000, do we? So, if you try and do an intersect right now, where one of your graphs is not on the screen, it won't work. So we're going to need to mess with our window settings. Okay? So I'm going to go into my window. Now, and this means this is something because I know kind of what happens, but I would suggest changing your X-min and X-max. Instead of going from -10 to 10, 0 to 20 might be a little bit better. I mean, you don't need the negatives, and you don't quite, it's not quite big enough if you just leave it at 10. So I'm just trying to save us a little time here. What about my Y-min and Y-max? We're going to have to go bigger than 350,000. Now, do I need to go 0 to 350,000? No. What I'm going to do is like Y-min of 349,000. I think I did 100 this morning. And then I did a Y-max of 350,000. 100. I should have done that a little differently, but that's all right. And then I'm going to regraph it. And now I'll at least be able to see two graphs on my equation or on my screen. Because we are zoomed in so much, my exponential graph doesn't even look like it's curvy, does it? It just looks like it's a vertical line, but that's because of the section we're zoomed in on. And then obviously my horizontal line is a horizontal line. Have I used second calc intersect with you guys before? I haven't? Okay. It's not difficult to use. You know how to find your zeros and stuff. It's similar. So if I do second calc, and you're familiar with this menu, right? Intersect is number 5, and that's going to find the intersection between two graphs. So my first question, let the calculator lead you through here. The first question is first curve. Is Y1 one of the curves I want picked? Yes. So Y1 is my first curve. That's just saying, okay, have I picked the curve I want? I'm going to hit enter. Then it says, okay, and this is the idea of if you have 10 curves graphed on your screen, which ones are you picking? I only have 2. So the second curve, do I want my Y2 graph? Yes, so I'm going to hit enter. Now it says guess. What do you think a guess is going to mean? You can just enter over it, usually, but it means move to the intersection point, right? And then you hit enter. And notice, what does it show an intersection point as? 11.77 and 350,000. So what's it saying? When x is 11.77, we're going to be at a y value of 350,000. Or in other words, in this case, when will the number of bacteria be at 350,000? at approximately 11.77 hours. So I'm going to say that it intersects at t equals 11.77 hours. Okay. That's the doubling. And I'm running out of time here. But, so example 4, notice the big difference is half-life. Instead of a base of 2, if we're going to have half-life, if doubling base is 2, for half-life, the base is going to end up being 1/2 or 0.5. Okay, so just kind of realize that's going to have a base of 1/2 because it's a half-life. Or think about it, it's 1 and you take away 50%, right? And you're left with 50%. Now, there will be one issue I'm going to have to work with tomorrow because this one is every 20 days is the half-life. And so when your half-life is every 20 days, you have to do an exponent that's slightly different of t divided by 20. So, like, I can show you if you want. The equation for this one is P of t equals 4 times 1/2 to the t divided by 20. And that has to do with because the half-life is every 20 days instead of some normal number. But do your homework for tomorrow. I'll help you when you get stuck, right? So page 270, 1 through 18.